All right. From beginning. All right. So I just wanted to kind of maybe go over the openQSE day, the schedule. There were some questions there, so I'll try to kind of cover the questions that we had. I'm hoping people here will be able to make it. We'll start the day with an introductory talk from Georgia Tesori. She's the ALD here. She'll just go over the ORNL quantum strategy. I'll give like a 10-minute just intro on the day so we can organize ourselves. Then we'll split up into 4 working streams. There will be 2 sessions. The first session will be from 9:45 to 12, so around 2 hours and a half or 2 hours and 15 minutes. Then we'll do a working lunch. Then Laura will give her keynote around 1 o'clock. And then we'll split into the second session of the working stream. The second session of the working groups. Then we'll do a report back. So the key point, I guess, is the 2 sessions here. Most of the day is going to be spent in the split out sessions. People are going to they can sign up for up to 2 working groups, and they can switch between the 2 sessions. So the first session, you can attend 1 working group, and then in the second evening or afternoon session, you can attend the second working group. Just to kind of highlight what the working groups are. So we have a software architecture working group, and that will be like focusing on the general software architecture. We kind of put out a paper recently. Then we'll go, this is going to be led by ORNL and AMD. The system architecture working group and workflows working group is going to be led by AWS. The compiler infrastructure is Josh and HPE. And then the quantum resource management is going to be IBM, and ORNL is going to be sort of like, we'll have representative in each one of those working groups. So I would encourage, we did send out a survey. It will be great if you guys fill it out because that will help us assign people to the different working groups. What's the goal of each working group? We're going to have milestones. So like each working group should define the next set of milestones to accomplish over the year. And I think another good goal to have is to define the interactions between the different working groups, because we're not going to be working in isolation. We'll need to kind of define the input and output for each of the working groups. So this is something to keep in mind. I'm hoping we'll communicate this with the organizers of the different working groups as well, just so that everybody's on the same page. Are there any questions in the general organization of the day? All right, sounds good. And with this, we'll switch to start talking about the different repositories in the GitHub organization, and I'll hand it off to Thomas.
Okay, give me 1 second here to find the right window. I believe this is, are you guys seeing a share now?
Yeah.
Okay. All right. So people are popping in, so we'll admit those as we go along. So I'm going to highlight a couple that are in the openQSE repo here. There's one that's not in this repo, it's elsewhere. It's some work I've been working on elsewhere, but they're kind of getting at the same thing. So that's why I wanted to bring them up here. Ultimately, they're going to meet in the middle, but we're sort of trying 2 different approaches and bouncing some ideas off. But the intent of these, so the first one here is QHW data. And the intent is sort of a representation of hardware data in a sort of portable, vendor-neutral format is the idea. And so in the other project that I have, it's called QTopo. It's another thing, but it's modeled after the idea of hardware lock or HW lock. But both of them are trying to get at the schema for what's going to be representing the platform pieces in a sort of vendor neutral way that you can bring that up. And each one's trying some different pieces on. And the thing I like about these, the QHW pieces that Amir's been pushing on this, is it's a nice installable Python package. The intent would be you could embed this in lots of things and then build your tool on top very quickly to just instantiate and bring it back to that standard schema format. And so there's an additional repo called QHWIQM, which is an instance, sort of like a use of that. So the intent would be is the data one has the schema, which is normalized, and validation pieces for that, maybe some examples on how to get to use this. And then this is sort of an instance of that, using that code to do an IQM version of things. So basically filling out the structure in the neutral way for data gathered from an IQM instance. Both of these are pip installable kinds of packages, so they're a proper Python piece, so you can bring them in and easily bring things into the environment where you're working on this. So a handful of elements from this that are there is it includes both the description of the platform, but also some of the elements like calibration, but also results from things you're coming out, including that as far as the schema of that. And one of the things that I recognized when we chatted about this that I was leaving out on the other approach that we were sort of working toward the middle is that was more of a monolithic approach that I was trying with QFW, the QTopo, and I like this element of being able to embed things, so a library plus a tool. Also sort of coming up with a normalized way that you can represent things that are not device specific, but you have to have some structure. And so, for example, if those who are familiar with HWLock, in that case, like everything's basically assumes it's a PCI device, and so you use levels of the PCI structure to give you that base framework on where to place things and how they're connected to each other and sort of like that. In this case, we're both using like a graph and sort of figuring out how you want to connect that. That's where we're starting to play with that, and starting to what elements need to be in the graph and how they're connected and so forth, and have accessors. So I just wanted to raise it here. I think this is work that going forward we can hopefully people can contribute to, and we can sort of make it a common format that that will make it easier to share and leverage. So those are the two I want to highlight there. Amir, you think I should pause here or go to the next repo? What do you think, time-wise?
Up to you. If people have questions, they can raise them now.
Okay, yeah, if there's any comments here, otherwise I'm going to move to one other project. It's unrelated to these the topology related things. Okay, well, and we can bring these up later. So I'm gonna hop to one other. So this is a chunk of work here. We expect this to also feeding. For example, the first use case was compiler people trying to pull out what are device parameters for different gates and different things like that. So bringing that information up in a normal manner and would be a good example for where I think that could be used. All right, so this is a different approach. So what this is basically this provides the intent here is to have a local developer cluster that you can use to instantiate. It builds off of a previous project called Slurm Docker vCluster, which I picked up from somebody out in the community, and we modified for another project. And then Amir saw it and said, "All right, let's make this better." And so this has been adapted yet further. It's got updates for Rocky Linux for a more recent version, but the gist of it is that you're containerizing your little HPC cluster. So after you do a Docker compose up, you get a Slurm control D, you get a database that's storing the results of your database, your cluster. You have a couple virtual compute nodes that'll stand up, and then they all talk to each other. You have a little, SSH between the two, or however you're choosing to stitch them to connect to each other. But the point is it's a little virtual Slurm cluster in Docker containers. And so this was extended to now have QFW support, so that you can basically have an additional container and the necessary connectivity there. They're all on their own little network to have QFW framework installed, as well as the QRMI and the QDMI enabled, so you can play with those resource pieces for the resource management. So submitting jobs, having those pieces on the back end, and having the base command, so you can start this up, tear it down, drop into containers if you need to look around and work on things, submit jobs, test things. Useful for CI pipelines, also useful for development, handful of things like this. So this is one of the projects that's in there. And the intent is really it's a developer tool to help you look at and work on these, getting a stack up quickly. I think those were the main things I wanted to mention on this, and I think some other things Amir's going to talk about are some of the pieces that are in this version of things. Is that right, Amir?
Yep.
Okay. One thing I'll mention here is this version has been extended to include the Slurm REST-D, which is a REST interface on top of Slurm. That I don't know that was sort of an experimental piece that we were working on elsewhere. I don't know that it matters, but I see it in the directory here. You'll see some droppings from that from the past. So with that, I'll hand it over to you, Amir.
Thanks. Any questions there, or should we move on? All right, moving on. Do you guys see my screen? Thumbs up.
Yes.
Yep.
Yes.
So next we'll talk about what actually runs on this Slurm cluster. And that's the quantum framework that we've been working on, and I'll give a quick overview of what that is. So the quantum framework is really kind of composed of two different major pieces. There is what I call the distributed execution framework, which is a C wrapper over Python. It embeds Python in a C program, and that C wrapper provides communication infrastructure to allow different instances of the DefW processes to talk to each other in a standardized way. It also provides an extensible RPC layer, so you can add RPC messages easily. It uses Swig. I don't know if you guys used Swig before. It's just an infrastructure to allow Python to call C functions or make C functions wrappable so that you can call it from Python. One of the things, or some of the future work that we're planning on this, is to integrate it with libfabric. So right now, the communication infrastructure is just like a TCP/IP layer that I wrote, but I think it will be more effective to integrate with existing libraries like libfabric, which allows you to communicate over different networks. We want to try to improve the RPC mechanism and allow this to be, right now it's very Python centric in a sense, so it supports running Python applications, but we want to be able to extend it to just as a C library so that you can link against it and use that same infrastructure from a C program or a C++ program. I wanted to kind of quickly maybe jump in and show you what kind of structure it looks like. So in there, is this big enough? Can you guys see it, or having a hard time seeing it?
Yeah.
Fine. Okay.
It's good.
All right. So the source or the base C code is in the source directory. So this has all the C code plus the Swig wrappers that allows different Python to call into the C infrastructure. And then inside the Python directory, you have basically the Python infrastructure that runs inside the Python interpreter that's in the C program. And this has like the infra directory has all the infrastructure pieces, the Python infrastructure pieces that allows the framework to work properly. The one that I want to sort of like kind of hone into so that we don't spend too much time into it in here is the service APIs and the services, because this is the important piece. This actually the infrastructure allows you to define external services and service APIs and services. So for example, we have, like, I'm in the QFW directory right now. So if we look at this, you will see that it has also a service APIs and services directory. So if we go into the service APIs, right now it has a couple of APIs that you can use. And let's look at this one. This was the relevant one. So if you go into here, there is this file, which basically defines the interface to the quantum platform manager. This is equivalent to the QRMI and QDMI. And Doug actually is doing a lot of work in this area. Doug Ocherek is doing a lot of work in this area, and he will present on it later, at a later date once it's more complete. But basically, this allows you to define an API for a service. So all you need to do is create a service API and the equivalent service process or service file, and then it will basically be able to, your application that you run, your Python application that runs, can call these APIs, and they automatically get executed on the service side. The way that's enabled is by this base remote class. So once you have that inherit from that base remote class, all calls into these functions basically become RPC calls that get executed on the service side. So you have, for example, here, just to kind of quickly go over a couple of these, you have a sync run, which allows you to run a circuit synchronously. You have an async run, which allows you to run the circuit asynchronously. There's a completion queue that you can read. So once a circuit completes, it gets the results get added in the completion queue, and you can read it or you can peek into it. You can also register event notifications, so that allows the service to actually notify the caller once a circuit completes, so that you don't have to keep pulling a completion queue. And there's a bunch of other stuff in there. If we look at the go up one, and we look at the service, sorry, CD services. So here you have different services that implement that same API. So we have one for quantum brilliance, for example, one for the simulator, TNQVM. We have one for NWQSIM, but we also have one for IQM. And the one for IQM allows you to talk to the IQM IQM system that is we just installed in Oak Ridge here. So this is just a quick overview of the DefW and the quantum framework. Cover this. Oh, one thing that's worth covering is I'm not sure how familiar you guys with PERTE. PERTE is a process management service. Because when we started this work, we didn't have real hardware, so we used simulators. So we wanted a way to manage a cluster of a simulation environment that's composed of multiple nodes. So instead of writing our own process management, we use PERTE. PERTE is the back end for MPI. So you can use it to run different, you use it to manage the simulator processes. So we don't have to do that manually. So quickly, what actually happens when you run the framework? Using Slurm, you can allocate two sets of resources. You can allocate the classical resources and the quantum resources. The quantum resources itself can be a set of classical nodes that run your simulation environment. And once you have both allocations, the application, the framework gets initialized first. And when the framework gets initialized, it starts the services that are required to discover the different hardware or simulators that are available. So it starts two primary services here, the service directory, and then the QPM daemon, which is the Quantum Platform Manager daemon. The QPM daemon registers with the directory service. This allows the application to discover those services that are available. And then from there, you can connect to that service, and then you can call the APIs that I showed earlier on. the QPM, the QDMI library and QRMI library, this is the work that's currently going on. I'm not going to go into a lot of details because we're going to present on it at some later time. But basically, this allows you to call into the different hardware, whether it's IQM. It depends if you have, if you implemented the interfaces for IQM or IBM or any other hardware, you basically are able to call those APIs that are presented by or implemented by the QPM daemon, and then you're able to run the IQM system, run on the IQM or the IBM. I'm actually going to show. All right, before I show a demo, I'll just kind of highlight some of the future work that we're looking at. We want to integrate with okay, so maybe this is a good point. Right now there is no runtime. Basically, we use say Qiskit, and then we wrote a backend for Qiskit, and then that backend directly calls the QPM API. What we want to move forward to is have a runtime layer that is closer to the application, and you don't have to deal with the QPM directly. And it also allows us to say, for example, use Qiskit to only build the circuit and then use the runtime to execute instead of going through a backend. This is an experimental idea we're kind of exploring right now, and we're going to talk about that in the July 24th day a little bit more. But right now, AMD and ORNL are working on this runtime to handle quantum workload. So we're exploring this, and we're going to present on it during July 24th. There's also a group that's IBM and ORNL and openQSE and others are working on the resource management and interfaces. So the primary goal here is to try to unify the quantum resource interfaces. But also look at integrating with multiple resource managers. Right now, for example, that environment that we have is a Slurm, that virtual environment is a Slurm, but eventually I'd like to have a Flux1 and LSF1. I'm not sure how LSF and PBS Pro because they're not open, but like if we have some sort of environment where we can test these integrations on, that would be great. We want to try to incorporate job admission controls in the QFW. So right now, when you when you allocate the resource here, there is no admission control. You can just use the back end however you want. But in order to integrate properly into Slurm, you want to be able to actually not oversubscribe or apply some policy on the usage of the resources. So we want to have, like we developed locally, we have like another project that we're working on for rate-based and credit-based admission control. It's still closed, but we'll open it up soon. And then we also want to incorporate device scheduling. So right now, you rely on the device. So when you submit circuits to run, it just gets to the device, and then like if the device implements a FIFO, for example, then all your circuits get queued, and then it's run in order. But maybe that's not the best way to handle it. You might want to have different types of scheduling algorithms, maybe round robin if you have multiple jobs using the same device, or if you want to have shortest job first or longest job first. So we're going to incorporate these different scheduling algorithms in the quantum framework. The other thing is we want to do real hardware and simulator. So right now, we haven't tested multiple different hardwares at the same time, like support for multiple different backends at the same time. So we want to be able to expand to run on multiple multiple hardware simultaneously, or even a simulator. And we also another piece of the authentication piece, and the authentication right now, cloud authentication doesn't work very well for on-prem systems, so we're looking into how to authenticate properly. Right now, in order to use the IQM system, you have to go generate an API key. The user has to go generate an API key, then use that API key in the scripts. But if you're going through Slurm, how will that work exactly? Like Slurm has to control this. So we're looking into how to do that right now. A couple of things I want to note. So here there's a high-level design that we started writing, and it's I just want to bring it up because it's a draft 0 right now, and it's supposed to be a follow-up from the archive paper that we put out. I want to open it up to the community for people to comment and add extra stuff to it, however they like. So with that, I'll jump to a quick demo of the Slurm. So right now I have an allocation actually on the Slurm environment. So if you do sinfo, you can see that we have two two systems that are allocated, 1 and 2. Actually, is it SQ dash U? Yeah. So right now I have C1 and C2, right? The way the framework works is you can, if you look at the framework, this is the quantum framework. So if you go to a folder called setup, and then you can do QFW activate. That will you source it. Sort of it's like Python. So you source the QFW activate. That activates the QFW. Then you can go, for example, to examples where you have a bunch of examples that you can run, and the simple one is the QFW Qiskit simple, which runs a simple Qiskit script with nwqsim as the backend. So here you can see this is initializing the framework, and then afterwards the actual script runs. And then once the script completes, it outputs the results and shuts down the other the services pretty much. So what does this look like? If you look at it, it's a simple script. All it does, it imports the QFW backend, initializes that that's a Qiskit circuit. It initializes the QFW backend, then creates a circuit and just runs the circuit afterwards, 1024 times. So that's simple. One other thing I wanted to quickly show is maybe I can actually show it here. So we have this Q hardware characterizations. It's a set of scripts that we wrote to characterize the timing of the IQM system. So they're available online, and you can run them actually through the quantum frameworks, or you can run them separately. So just an example, you can go into Q hardware. I cloned this is all within the Slurm virtual environment. So I went into the quantum hardware characterization, what do you call it, directory, and then I'm going to just pick the smoke test to run. That will actually run the circuits on the IQM system from my virtual environment. So right now it's running. So if I go to the IQM server itself, in a second you'll see it updating with the circuit that it runs, hopefully. Right, so you can see now it created, like it actually ran a circuit here, 100 shots, and you can see some results. Now, if you look, what this guy does, it gets all the output from the IQM system and puts it in data and like a bunch of directories under there, but all the results are here. Right, and in this case, for example, you can see that it outputted multiple things, including the result that comes from that's the normalized result. So we're like the repositories that Thomas talked about, the Q hardware data and the Q hardware IQM, they're being used in the framework here. So the the IQM returns the results that are IQM specific. Then the framework takes that IQM specific results and converts them into the common format and then outputs it. So if we look at this guy here, that's the normalized hardware, normalized data that comes out of the results. So you can see, for example, it ran a bunch of things. The interesting part here is the timeline. It shows when it was created, when it was received, when the validation started, when the validation ended. So you can get a timeline of the execution of the entire job on the device itself. Again, this is like we only tested this normalization path with the IQM system, but hopefully we're going to work with other vendors to grab the data that they have, and then we'll try to create a structure that normalizes this data from multiple different vendors. Anyway, I feel like I talked enough, so I'm gonna stop here and open it up for questions if anybody has questions. Go ahead, Jerry.
Yeah, I was able to explore recently the QFW Slim cluster. I think it's really nice. I was able to run things as a developer, with the Mimic device. So I think this is a lot of good work, putting things together. I have some questions or opening it for the floor. So some of the implementation choices, right? So in the schema definition and in the server and services definitions, what's the rationale for the technologies you chose or that were chosen? Some of the member companies use protocol buffers, gRPC for services, and from my experience, they have proven pretty useful in kind of doing language agnostic definition. A lot of the server client sub definitions set up for free. So any thoughts on that, or doing streaming RPC stuff like that? So any thoughts on what that might be?
This is actually more historical. So this the
Okay.
DefW is something that I created a while ago, and then I reused
Right.
it for this type of thing. So at the time, I just created my own RPC. So the RPC that I created just converts your function call into a JSON file. You stream that JSON file to the service, to the other side, and then the JSON kind of you can convert it back into a function call and execute it on the other side. I agree with you. Can use different technologies that are more standardized. So this can be the next step. So if you have the time to actually help with that, that would be great. Yeah.
Yeah. Thanks. Yeah, but I think that the picture, the architecture, when you run a Qiskit application with a backend defined as openQSE infrastructure, if you will, and running it with Therm is super useful, right? And the choices make a lot of sense given sort of the the stage where we are in the definition and exploration.
Yeah, and I'm open. Like if there are other ideas of how to implement some of these things, I'm not like glued to a specific implementation. So we're always looking to improve. So there's ideas you can either push a PR or maybe even like comments and suggestions. That would be great.
I think ultimately is what the member companies or the members of the openQSE community think is most appropriate, right? I mean, in observing some of the physicists using Python and using JSON as the exchange format is useful, but it sort of doesn't lend itself to writing sort of a strongly typed or sort of a reliable services or components, right? So that I mean, but again, this is just my opinion, and others should chime in. And depends on how they do things. Most of the job submission, etc., has sort of a REST flavor. QDMI has sort of a different approach, right? But that depends on what the community thinks.
Yeah, and fair. I think one last point I'll put there is the idea of the framework is not a product ready thing. It's supposed to be an experimental environment where we can try the different interfaces that we kind of come up with. We try the different technologies, and hopefully, as we progress, this might turn into a productized environment where it pulls the different components that are being developed in the community in one cohesive stack. Go ahead, Smriti.
Hi, yeah. So I had a question related to Swig that you had mentioned before. So how are you connecting to the IQM device here? Is it using Swig? Is it using an API?
Yeah, no, it's using, so Swig is just used internally to allow, Python functions to call C functions, and that's internal to the DefW, so it's not used externally. Maybe I can show it quickly. So for the IQM device, we developed an like a specific service here. So if we go to this guy, and then we'll go to the svc qrc.py, you'll see that here we're actually we're importing the IQM service client, and in the IQM service client, we are actually calling the APIs that come with IQM directly, right? Like when you run circuits, you call IQM.run circuit that actually goes and runs the circuit on the IQM device. What I didn't show here is we have two environment variables set, one with the API key and one with the URL of the IQM device that is local in what do you call it, in Oak Ridge here. So to kind of answer, the way we talk through to the device is through a layer that we created. Now, to add QRMI and QDMI both have ways to talk to the IQM device using the same method. So we're in the process of testing those as well.
So you are not using Swig for that though, right?
No. We're
Okay.
talking because this is a Python module that
Right.
IQM provides. So we're just calling it directly from Python.
And so,
Yeah.
I mean, I do have like this idea of making this vendor agnostic. So, yeah, there could be like a specific service which could handle all of these connections for different APIs, and it could make it vendor agnostic.
That is what we do here. So if you go in the service APIs that we're just talking about, right? So this is your vendor agnostic layer. So here, the application never calls directly into the IQM service or anything. It just calls async run or sync run. And depending on how you select, so right now we have multiple different types that you can select when you instantiate your backend. You can tell it, I want an IQM, for example, or I want an NWQSIM or a QB or just a simulator. And you can also say, I want superconducting only. And if there's multiple superconducting, it will return one of them. But then you just call sync run and async run and other APIs here that are common. And then that gets translated into whatever backend call that the service implements. Again, this is very similar to what QRMI and QDMI, and that's what we're trying to do. We're trying to kind of converge on one final solution or final API, and then the implementation behind that API can be QRMI or can be QDMI or can be something else that implements that API.
Yeah, no, I mean, even at Dell, like we do it similarly for our orchestration software. So, which is why I was thinking how it is implemented here. Makes sense. Thanks.
So, yeah, so to connect kind of my point earlier, right? Sort of Swig and it's just a way of connecting Python linear to a C implemented service, right? I mean, and so this definition is sort of at the moment done by hand, defining the interface, right? And kind of in gRPC, right? It has a interface definition language. They're kind of agnostic to a specific implementation, and that allows one to define the RPC service, the calls, and the request response. And data structures, and that's for that to be as a payload uses protocol buffers, right? So that's a sort of a complement to what it is, but indeed in here Swig is just a way, if I understand Amir correctly, from getting something in Python where Qiskit is obviously Python based, and getting a Python based calls from Qiskit into services written in C++. Is that right?
I think there might have been a confusion about Swig. So Swig is used internally inside the DevW itself. It's not used to implement the service that I'm showing here. This is entirely Python, quote unquote, right? Yeah. So here, sorry, go ahead.
So you define the services though in a sort of a written API class in Python, correct? Yeah.
Right. Yeah. So here, you define the service, but you don't have to do anything else. All you do is you define the service or your API here, and then on the other end, you define the implementation. And because you inherit from that base remote, which is infrastructure piece you don't ever touch, it automatically makes all your calls basically RPC calls. So inside here, you can just put any parameters. Like there is nothing that you need to do, not like gRPC where you have to go and you define your protocol buffers and how they look and stuff like that. Basically, all this is done for you by inheriting from the base remote. So then you can, I can change this to be anything. I can change it to take any type of parameters. And then as long as the service end looks exactly the same, then when the application calls this, all these parameters are sort of switched. The function call and all the parameters are converted into JSON. JSON is sent over to the service. There's a reverse sort of translation from the JSON format to the actual API call, and then the execution happens on the service side. Go ahead, Thomas.
So, Jiri, is the point you're trying to make is what this assumption is here is that our interface definition is in Python, whereas a gRPC, if I understand correctly, you can generate the bindings. You have a sort of generic definition language that then can be generated to the target binding language.
Exactly. You know, in IDL, in a gRPC that has a protocol buffers like syntax, not important, right? You define the interface. So basically the equivalent of what you have here is there, right? And the difference is that, you know, the gRPC mechanism is kind of assumed to use serialization digitalization of protocol buffers, right? But the definition and the generation of the client stubs and the server stubs for implementing these things, right? I mean, implementing the stubs are not, you know, fully implemented, fully featured pieces. But the point is, it does what the generation of a protocol buffer compiler from a gRPC service definition in IDL generates for you is the bindings for a given language, right? So the if I understand correctly here, you have a basically Python defined API for service. If the service is implemented in C, it uses Swig to go from Python to C, and the RPC and everything is part of the base class or you know, kind of a specific RPC package that you have chosen initially, right? You know, there are other packages like JSON gRPC, etc., but they are less efficient, etc. So you understood in a nutshell, you understood correctly, Tom, right?
Okay.
It's just it's an argument to be sort of a more language and implementation agnostic and and dovetailing with some of the companies, you know, in the previous things, companies use gRPC internally, although most of the services like the IQM and like, you know, IonQ API is REST-based because that's kind of the, you know, easiest one to do, but not necessarily the fastest or, the fastest in a, most efficient for having services communicate to each other over RPC.
No, and I agree with you. I think this implementation is tied to Python, right? And if you need to call into C, then you have to have some sort of a way to call into C using Swig or using C types or whatever. gRPC does give you the capability of not being glued to a specific language. So I agree 100%, and that could be an improvement that we can look into implementing. Go ahead, Inush.
Yeah, let me confirm, the assumption of this, infrastructure. So yes, yes, if the end user application uses a, bunch of computation, needs a bunch of computation resources for post processing after the execution of the quantum. So do we assume that, two, quantum job and HPC job is separated and the outside of workflow engine will control this kind of two job? Is that the assumption, or Cascade application can use or MPI code or something?
So in this setup, it can work both ways. So if you can, this allows you to only allocate one node, which is the quantum resource node. And if the setups, for example, I'll give you a concrete example. An IQM system that we have here, we have it comes with a Dell server. It's just a server that runs the software stack, and you're allowed and that's runs the REST interface so that you can submit REST to it. What you can do is you can make this Dell server as an allocatable resource, and then you can just submit directly, like when you allocate, if you want only a quantum resource, you just get that Dell server, and then your everything runs on that Dell server, including the submission of your circuit and then running on that circuit, and you never have to have another HPC node. So that's if you just want one quantum resource only. But if you want both classical, like some HPC node, and your quantum resource, you can do it the way I'm doing it right now, where you allocate an HPC node and a quantum resource. Your HPC node runs just a Qiskit application that can use MPI. And then because it knows about that service that is running on the quantum resource, then it can, as it runs, one of the MPI processes can decide to submit like a circuit, and then it basically goes to the service that's running on the quantum resource, and that service submits it to whatever backend you configured.
I see. Thank you.
Go ahead, Neil.
Yeah, I was just wondering, how this DEFW works with, Q at W. And also, I was just wondering that, do you have any assumption for DFW? Seems like there is a communication, backbone is already been included, where I think you're assuming some, high speed, network on top of it or not.
So the DefW is just, like I was saying, it's a C program that implements some communication. So right now it's just the TCP IP layer that I wrote myself. And then inside the DefW is running a Python interpreter. So when you actually run your application, you're executing your application inside that Python interpreter that's included in the DefW. That gives you all the glue that allows you to talk between different DefW processes. So my services that are running on the quantum resource are actually DefW services, right? So when the application runs within that DefW, like the Python interpreter integrated in that C layer, it basically allows the application to discover any services because it's part of that global infrastructure that the DefW provides you.
So why it has to discover the others application or services, because of the resource contention types of thing?
Well, how would you know who to submit to? Like if you allocated a resource, you need to find out that resource. You need to find out the endpoint for that resource. Eventually, what we're trying to do is we're trying to hide, like I said, the API key and the URL. The application doesn't really need to know anything about it. So all this API key and URL can be injected directly into the service that's running on the quantum resource side. And all the application need to do is call that common API. And then it doesn't need to know anything about how the actual request ends up being run on the quantum side. Does that make sense? Or?
Yep. Thank you.
Any other questions, concerns? Again, this is all work in progress. So, and the invitation is please submit PRs, please submit comments. It's the whole point of this is to kind of open it up to the community. Go ahead, here.
Yeah, I mean, sort of a protocol buffer strathole notwithstanding, I think, especially the TFW Slurm cluster is a very nice environment. And I think part of it is if one submits jobs through Slurm, right? The assumption is one is already authenticated to the Slurm control node, and one has access to the quantum resource nodes, right? This is a compute resource node or GPU resource nodes, right? In a general sense. And I think, but fundamentally, I think it's a different model where kind of, as you mentioned, the TFW sort of a node speaking on behalf of an IQM or any other vendor's device kind of has to have authentication, right? So one has to figure out a simple way to pass around authentication tokens or something, because eventually anonymity is important, right? So has to come through, whether it's Slurm, whether it's sort of a different way of sort of submitting things through the a REST-like API to the Slurm cluster. But I don't think that's a sort of surmountable problem. It's just a question of, connecting and translating various authenticators or having, IAMs, that's what that for, right? There are different services to figure out how to translate identity of, you showed up, you demonstrated SSHing into the Slurm control node, and then it assumed that it's your identity, and then you were able to submit and run jobs. So it just sort of, some extension is needed, but I don't think it's a big deal, right? I think, as you said, right, we encapsulate whatever the token would be in the, or the authenticator would be in the REST API like client for the device, and need to manage that the API keys being there are mapped to your stuff anyway. So those are not a big deal. I think those are important to answer and think about the architecture, but that's something to consider, right?
Fair. I think I want to stress the API key or the authentication to the device is not exposed to the application at all in this setup, right? I had to set it up manually, but it's only known to the service, to the QPMD service that's running on the device. So when on the quantum resource. So when the application calls the common API, it's not passing any sort of authentication keys there. It's just calling into the service, and the service knows about the authentication keys that then it uses to talk to the device. The key point is here, right now I had to set it up manually because we don't have a mechanism right now. But eventually, once you allocate your Slurm allocation, once you get your Slurm allocation that has some quantum resources, that process will give the service its key without any API, without the user ever seeing that key. So it will be hidden completely from the user. But we don't have a mechanism of implementing that right now because of the way the API keys are managed with the device.
But so architecturally speaking, indeed, right? So I was making the same point. Architecturally speaking, one has to have as part of the architecture, a service that translates from the identity of the user submitting job or using Slurm into the API key like things, because API keys are used by a few other vendors as well, right? And that nothing else, whether it's AWS or whether it's for IQM or it's IonQ or Continuum things, all of them are basically authenticators associated with some identity, except that outside of the realm of the IQM device, there's no way to connect that API key to your identity, whatever that may be, right? And so we need to think of something that's sort of a pluggable, and there are infrastructures for that, right? This is not the not the problem that we need to solve. It's just that something that you should account for in the architecture and kind of make explicit that binding between the user's identity who's running the application, patching it through all the way down to the API key needed for running a REST API for device X. That's all, right?
100% agree. And I think the difficulty here is we need the vendors to provide some mechanism for that as well. It's not like a complete something on our end that we have to manage. The vendor has to provide the centralized key management.
Correct.
Go ahead, Mike.
I had a question about sort of about the scheduling. You were mentioning that you could, I think you were saying you could use Slurm to allocate an HPC node and a quantum resource if you wanted to, or you could allocate just the quantum resource and then run your Qiskit Python program on the quantum resource. What I was
sorry, I just want to, if the quantum resource allows you has set up has the same setup as the IQM where it comes with a node that you can access. Otherwise, you'll have a quantum access node that you have to configure in the system. Sorry, go ahead.
Right. But my question is, if somebody's writing an application where they want it to be a little bit more like what I would consider the usual cloud model, where when you're using Qiskit, you tell something to run and then it goes off and waits in a queue or whatever and all of that. Does that fit into what you have already with QFW, or is that you would use the cloud model entirely and kind of go outside of all of this, or what do you think about that kind of use case?
So are you talking specifically about our deployment here, where are we going to allow cloud-like job submission?
I'm curious about that, but you can answer it about the specific deployment or the general direction. But it's sort of a question about if say a user's writing an application in Qiskit and they want that behavior where they construct a circuit and then they go when they ask to launch it, it goes and waits in a queue somewhere to do so. Does that fit into here, or would we have to like make a Slurm allocator shim or something inside of QFW to get that behavior?
So right now, when we wrote this, we wrote it specifically for a Slurm deployment. So that's what we're focusing on. So we need to allocate a Slurm, it operates within a Slurm environment. I agree with you that if you want to just operate as cloud, some work needs to be done to the framework in order to enable that use case. And shouldn't be too difficult, but it's not free right now. We have to do some development effort together to work.
Yeah. What I meant by bringing the cloud part in is just that the relationship with the scheduler might be different, right? They might want to have waiting in the schedule queue before running their circuits. Not necessarily that the mechanism to do that should be the cloud API. It could do that through the cloud API, but not necessarily the solution. Anyway, thanks.
So just to kind of understand this, when you say the scheduler, you mean on the cloud provider side? So you submit the work and then it goes on a queue, and then there's a scheduler on the cloud side that allocates that and then runs when it's free. Okay.
Yes, and if you've got kind of the quantum resource completely managed via Slurm, then you have to make an equivalent sort of trip through the Slurm scheduler in order to have that functionality.
Yeah, and I think what I've been trying to do is I've been trying to modify the QFW not to need a Slurm environment. So once that's complete, then it should be able to submit, do what you're talking about. Although I have to, still it's not free. It's some development work that needs to go into it. Sorry.
Okay, thanks.
Thomas?
This one throws back to a few points earlier, but it's not immediately in here, but the pieces are in here for the Slurm REST for the token, so you can generate tokens and actually have a RESTful interface to talk to Slurm. So for this submit pieces to I think your comment earlier, Yuri, we could add that. The reason that was added for another project was because we had center-wide pieces that were talking from a cloud interface and needed to pass tokens to run on the back-end resources, and we were working with that, and they had their token on top that would need to pass through and basically did the same job description through the Slurm SD. And so that's what that work was there. So you could imagine putting that same sort of thing. And so the existing platforms, that already have facility level, job submission token stuff would just be talking down to this one. So it's a layer below that. It would be that's sort of like my thinking on like how that could fit together. You could sort of dummy that up pretty quick.
Understood. Thanks.
Any other questions? I think we're up. Our time is up. Awesome. Thank you so much for taking the time. Again, this is an open invitation for anybody to download the stuff, try it out. Don't like it, submit PRs, suggestions. It's an open source project. Thank you, everyone.
Sounds good.
Take
Take
care.
it easy.